it's aimed at provide you an overview of the ESO facility. And the first speaker is Bruno Leibundgut, the VLT program scientist. Please, Bruno.
Good, let's try this one. Good afternoon, everybody. And so what I'll do, I'll expand a little bit on what Michael has done already. So I'll give you an introduction to ESO and what ESO is and what it does, I think. This is similar to what Michael showed you. This is just a collection of the various facilities that we have. Just to show you, in the middle, there's the VLT up here on the left. This is the Vista telescope. This is the sun setting behind Paranal here. Here's La Silla, sort of the original observatory that ESO has built. And then we have Apex on Chahnan Tor, which is placed next to ALMA, which is also running on Chahnan Tor. This is a classic Chile picture. So you have these volcanoes in the background that are typically 6,000 meters high. Chahnan Tor itself is already at 5,000 meters altitude. And as Michael said, we will also build new telescopes. Well, in this case, we will be involved in a new telescope array, Cherenkov telescope array, which uses the Earth's atmosphere as a detector for very high energy photons, and the ELT, which is going to be built on a mountain not too far from Paranal. Okay, so I have a short introduction to all of those sites. In a sense, you can separate ESO in an optical part, optical telescopes, optical near-infrared, and then some mid-infrared, and then the sub-millimeter, millimeter telescopes, Apex and ALMA, and then in the future, a very high energy telescope. So this is the original La Silla mountain range. So this goes up here until you hit the 3.6, which is the highlight of the mountain. It's always been the highlight of the mountain. ESO only operates 2 telescopes on this mountain at this point, the 3.6 meter telescope and the NTT, which you can hardly see back here. The other telescopes, some of the other telescopes are still operational. They're used by national communities on a private basis to do some specific experiments. This is Paranal Mountain. As you see, ESO has the tendency, this is true on the 3.6, this is true in Paranal, and this is also true on Armazones. ESO has a tendency to chop off mountains. So we always have these beautiful mountains that have a peak, and the first thing we do before we even put a telescope there, we cut off the top 30 meters typically to make space for the telescopes. And you see this here, there's a platform here. So this mountain was a beautiful mountain that had a peak. We cut it off so that we could make space for the telescopes. Here are the 4 8-meter telescopes. I'll show you more of this. There's a control room, etc. I just want to point out this volcano, which is at the border to Bolivia, and it's 180 kilometers away. And so that tells you a little bit about the clarity of the air, how easy it is to see that far. Now, if you see that far towards the horizon, you can imagine that you can see very well up into the sky. So here's a picture of Apex, the Atacama Pathfinder experiment. It's a 12-meter antenna, up on Chahnan Tor. This is the plateau at 5,000 meters. This is the moon rising behind Chahnan Tor Mountain, which is another one of those 6,000 meter altitude volcanoes. A picture of ALMA as it is operational. I will not talk too much about ALMA, so let's just move on. An important part that Michael has already raised is the archive. The data that we acquire with our telescopes goes into an archive. All the data that we acquire goes into an archive. And that archive is accessible to you from your desk, okay? So if you find a desk and a computer, you can access the archive. The ELT is under construction. These are the headquarters here, so this is where you are. Marina already showed you where you have to gather when the fire alarm goes. That's up here in the parking lot. These are the new extensions. This is an engineering building, a technical building, and these are offices that were created a few years ago. Fun fact about ESO, the shortest line between 2 points at ESO is always curved. It's never a straight line. And ESO has a representation in Santiago, in Vitacura, which is a suburb of, well, it's now part of Santiago, where we have offices as well for people to work. And opposite this place, there is the other place, this here, which is the ALMA operational center, the joint ALMA office in Santiago, which is also run by us. Okay, so Paranal, here's a picture of Paranal in a slightly different way. So you now can see this is the road that leads up to the mountain. At night, it's closed here, so you have to turn left and you have to park in front of the technical and operations building. These little dots here, which look like the spaceship in 2001, Space Odyssey 2001. When you come up and the lights are on in here, you do think you're in a spaceship, or you see the spaceship. That's the control room from where you control these telescopes. And you can control those 4 8-meter telescopes, this 2.6-meter telescope, and this 4-meter telescope back here, all from that one room. And then in addition, we have these movable, so these are fixed, but these are movable telescopes, 1.8-meter telescope each, that can be moved on that platform. You see a little bit with the white stuff here, those are rails on which they can move. So that's the situation of Paranal today. What I've done here, I've labeled all the telescopes with the instrument names. You don't have to read those now. All I'm telling you is that right now we have 12 foci. Each telescope has 3 foci, and all foci are filled with instruments. And we have instruments everywhere. There's this little thing, the laser that goes up into the sky. I'll tell you a little bit more about that a bit later. This is one of the unit telescopes, as we call them, one of those 8-meter telescopes. So down here, which is hard to see, here across is a mirror that has 8 meters, 8.2 meters across. And as Marina once told me when I was there with my family, she said, the surface on this mirror, that's not true anymore. But at the time, the surface of this mirror is bigger than my apartment. Okay, so the surface of this 1-unit telescope mirror is 51 square meters. Okay, you can live on there. Well, no, you can't. Not on this one. Anyhow, we wouldn't let you. So this is the 8 meters here. So 8 meters is big. You know, 8 meters is almost from here to that wall back there, and then you move it. We'll not talk about the 40 meters. So in addition, we have these 2. We have a golden telescope. This is given to us by the Brits. Well, it wasn't given to us by the Brits. They had to pay for it. So this is Vista. This is 4 meters across. This is one of the survey telescopes. And this other one is the VLT survey telescope, as it's named, VST. This is 2.6 meters across. And again, it's the survey telescope. These 2 telescopes scan the sky essentially almost the whole, well, they both have programs to scan almost the whole sky. This is what they do. This is the infrared, the Vista telescope. So one survey that we have there is VHS, which is the Vista hemispheric survey, and everything below that blue line is covered in that survey. So if you need any picture in the infrared on the southern sky, it will be in the archive, in the ESO archive, and you can find it there. So that's one of the things that this survey is doing. Then they picked out some interesting targets. There's the VVV. This is a variable survey or search for variable stars in the bulge. And some of the proponents, some of the main actors in that survey are sitting in this room. So there's the bulge here to look for variable stars. And then you have this extension in the galactic plane. We have the Vista Magellanic Cloud Survey. We have then extragalactic surveys, Viking here and here. We have these 3 fields of video. And up here, there's a tiny field which you can't see, which is Ultramista, which is a very, very deep field in the infrared. And the same is true for the optical. So that's the VST. There's a survey, VFAST Plus in the plane. And you have these other extragalactic surveys, KIDS and Atlas, which is finished now. So I'll talk about a little bit about opportunities that you have at ESO. What do we offer? What are the things that we believe were actually kind of unique, or we do maybe better than other people do, or things that will help you in doing your research. So we have 4 8-meter telescopes, which is actually more than anybody else has. Now, the European community is a very big community. Adding Australia, we are a very big community. So 4 8-meter telescopes is just enough. We need the 4 for another reason as well. But we have 12 instruments, as I explained to you. So we have a lot of flexibility. We have what I would call a very high scientific throughput. Michael showed you the number of publications that are produced with ESO data, with data from our telescopes. I'll show you the same graph as well, because we would like to show that graph. But roughly, we offer to the community of the order of about 1,200 8-meter nights per year. Okay, so that's the equivalent. That's essentially the equivalent of Keck plus Gemini together, except that Keck and Gemini have only 1 telescope in the south and 3 in the north. Now we only have them in the south, so pick your choices. The other thing which Michael has showed you in great detail, very complicated, we do have what we believe is a very successful operational model. So we do have a way to help people to get access to observing time and to make best use of their data. So we have a model that allowed new modes. We have high time resolution photometry and spectroscopy. Some of this actually we stopped because there was no demand from the community. So we did introduce modes for opportunities that the community could take. Now, if the community doesn't use it, we actually take them out again because we can do probably something better for you. We have a mode of what we call fast turnaround currently. That's a DDT channel, the directed discretionary channel. Ask more about this if you want. And we have a close interaction with the users. Some of this is done through what's called delegated remote observing, which is a mode that we're experimenting with right now. We offer a system that has spatial resolution from 1 degree, that's just the largest field of view of some of those survey telescopes, down to it's 2 milliarc arc seconds. Actually, we do almost better than that with gravity. We have a wavelength coverage, so we can offer you observations on the sky from 320 nanometers, 3,200 angstroms, if you're old like me, to up to 20 microns. Okay, so we have instruments that cater to all these wavelengths, and we have spectral resolutions that come from a few, just filters, maybe unfiltered observations, all the way to 100,000 and pretty soon 200,000 spectral resolution. And Henri Boffin, Monica Peter, and Christian Hummel will tell you much more about these things than I do right now. This is essentially what I said. I'm going to skip this. I just wanted to display to you just 2 examples of why multi-wavelength astronomy is so powerful. Okay, this is an object on the sky that most of us have observed. This is actually that you can observe something you can observe as an amateur astronomer if you have a decent telescope. It's called the Helix Nebula. This is in the optical in 3 different bands, and you see the beautiful structure in this planetary nebula in here. Somewhere is the white dwarf that ionizes this material. If you observe the same object, which is now not so easy as an amateur, if you observe the same object in the infrared, it looks quite different. And so the fact that you can use different wavelengths helps you in understanding the astrophysics that you're looking after. And so that's one example. Here's another example, which is Centaurus A, which is an active galaxy, fairly close. It's the closest elliptical galaxy to us. It's an important object. It has this extremely strong dust band in it. So here are the stars around it. This is just the inner core, as Marina would tell me. This is just the inner part of the galaxy. You see some star-forming activity up here, and you have this dust lane. Well, lo and behold, you look at this in the near infrared, it looks very different. Okay, again, now you see all the stars in here. You see the elliptical galaxy that's sitting in here, okay, very clearly, and you see that distribution of stars that's going around. This is like a tilted torus, or a warped torus, maybe better, that's going around that inner elliptical galaxy. And so this is, of course, the signature of the merger, presumably a spiral galaxy merging with this elliptical galaxy. Now you could do the same thing with ALMA. With ALMA, you now see the cold molecular gas. So you see something else again in there. You see that the elliptical galaxy essentially has no molecular gas, no cold gas, because they're too hot for this. And you see, in this case, you even see the rotation of those of that gas in that galaxy. Okay, let me see where I am. All right, I need to speed up a little bit. Yes, I need to speed up a little bit. So I'm not going to talk too much about what the contributions of the ESO telescopes are or have been to the various scientific topics, astrophysical topics that are undertaken with the telescopes. Henri, I think, will cover that. Well, we hope Henri is covering that. The one thing I wanted to sort of highlight a little bit is the exoplanet story. ESO, because ESO has so many different telescopes and so many different instruments, we can actually build up something that I call the ESO exoplanet machinery. Okay, so we can have HARPS on the 3.6 meter telescope, which is a high resolution spectrograph, extremely stable to look for radial velocity changes. We have adaptive optics instruments on the VLT that allow us to actually look at, this is blocked out the star, so you can actually see the planets around that star in this case. So this is with the adaptive optics system. We have VLTI, the interferometer, which Christian Hummel will explain to you much better. I won't do it, which gives us extremely high spatial resolution. And then we have some other instruments that help us with this as well. The other function that is dear to my heart is that we can actually observe objects over 30 years. So the VLT is a bit of an exaggeration because the VLT started operating 20 years after this exploded. But since the VLT is working, we've observed this supernova 1987A, every year, with one exception when the OPC didn't give us the time. But essentially every year we've observed this, and this is just a collage of those various things. Okay, I'm going to rush through this because this is only mildly interesting, but just to have that said, so thank you, Nanda, for sending me this morning. This is the number, this is a similar number of, a similar graph that Michael showed you. This is the number of proposals that we receive per semester, we call them periods, out to period 101, which was the last one. So the next one is period 102. And you see we receive of the order of 900 to 950 proposals every semester. 1,900 proposals per year. And underneath you have the number of COIs and countries. Let's skip this, I don't have the time. You've seen these graph already. Michael showed you this graph. This is the number of publications. We're of course proud that this goes up. The reason this goes up, there's two reasons that this goes up. One is our community is becoming larger, more people writing papers. And the other one, we offer more and more facilities. So we have more telescopes than, not every year, but we do have more telescopes as we go along. I'm going to skip this. I want to point you to this. The call for proposals for period 102, which starts on the 1st of October this year and runs until the 31st of March next year, is open. You can all apply. Very important, deadline is the 28th of March, noon here. Okay, not where you are, wherever you are, noon here. Oh, this is for Australia important. We checked this out. It's European summertime. Watch out, there's a 1 hour time change. Okay, anyhow, so that's the support that we give you, and we have talks by Henri, Francesca, Lowell, Michael, Giacomo, and John will bring this closer to you. Then there's support on data reductions. We have these tutorials that will happen on the instrument pipelines, and Wolfram, Lodovico, and John will tell you more about this. Science Archive, I wanted to mention this because this is the easiest way for you to get data. Okay, you only have to register, then you can get the data. So you don't have to write a proposal, you don't have to do anything other than register. This is just a graph of the current interface. Martino Romaniello is going to tell you more about this, I think, tomorrow. This is the same thing, again, in slightly more detail, so you have various ways to get access to the data. And this is the new archive interface, which, again, Martino will show you. So the archive has a major upgrade coming. I saw it the first time last Friday, and the first thing I said, when will it be available? Okay, so hopefully this is coming soon. Just a few other remarks. that go with ESO as well. There are ways to track us, to find out what we're doing, okay? And there's a number of those things. There is a student and fellowship program. This is for young people, of course. We have a visitor program. That's to older people. We have workshops and conferences like this, but we have also scientific conferences here. We have the ESO Messenger, this is a ESO Messenger, which is a quarterly magazine that ESO is publishing, so you can find out what's happening there. We have a science newsletter, which is roughly published once a month, and we have, of course, many web pages. So just very quickly, the studentship program is offered to everybody. No, you have to be a student, sorry. It's offered to all students in our member states, but also in other countries. We do have a slight preference for member state countries because they pay. So that's a slight thing. But the student spends 1 or 2 years in Chile. This is a picture of students in Chile. Slightly older picture, but still it's a picture in Chile. And there's also short-term opportunities available. The fellowships are postdoctoral fellowships. We have a number of those available, again, open to every nationality. These are 3 years in Garching if you come here. If you're selected, you come here for 3 years. In Chile, you go for 4 years. The reason is in Chile, you do research plus observatory work. You actually spend time on those beautiful mountains, which is great for a while, but it can be tedious. And so you get an extra year if you do this in Chile. In Garching, you don't get that. And we've just introduced technical fellows. The visitor program, there's even visitors in this room right now. So the visitor program is open to everybody. You can apply. I believe we've now changed the system to have 2 deadlines. Is that right? Well, whatever. In the past, you could apply anytime. Just try it. Okay. Somebody will tell you if there's a deadline. And so you come either to a place in Santiago or you come here. Old picture. The ESO Messenger is a magazine that's available. There's printed copies out at the entrance, but you can also access it on the web. Okay, so it's available. It's actually available on the web slightly earlier. So these are the latest issues. I know the next issue is being made this week. And the ESO newsletter is, again, something that you can sign up. You sign up on the web, you go to the ESO portal, you sign up, you get that newsletter sent to you whenever it's issued. For example, this workshop has been advertised in that newsletter. Presumably, many of you have received that already. And that's it. Thank you.
Thank you, Bruno, for this nice overview. Is there any question? Don't be shy. No? And from Australia, is there any question? No. So the next speaker